Okay, so this time we're looking at something specific called a permutation. Now on your handout, under the word permutation, you have 2 bullets. And so you are going to actually write down what those bullets are, the characteristics of a permutation. The first one is that no item is used more than once. So notice we already have something that's different about the last type of problems we did. So in the license plate problem, we could use a letter more than once. But in this one, no item is used more than once. And also, the order of arrangements makes a difference. So ABC is different from CBA. The order makes a difference. It might be the same 3 letters, but you've made a new arrangement when you've reordered it. Now, the other thing that I don't have here in this PowerPoint is that you're taking from one group of items. So based on their long-standing contribution to rock music, you decide that Rolling Stones should be the last group to perform at the 4-group Offspring, Pink Floyd, Sublime, Rolling Stones concert. Given this decision, in how many ways can you put together the concert? Now, this problem can actually be done very similar to what we already did with the fundamental counting principle. So how many groups do we have that are going to perform? 4. So we have 4 spots, if you will, to fill for this roster of the concert. And so similar, you can do, okay, the first person to perform, the second person, the third person, and the 4th person. But this time you're picking from one group and you're trying to figure out how many choices of bands do I have for each slot in the concert. Now, what did we decide about the Rolling Stones? They were going to go last. So how many choices do I have for the last spot? 1, because definitely Rolling Stones are going to go last. Now, how many bands are left after I've made that decision? 3. Does it matter when they perform? No. So how many choices do I have for them to go first? 3. Okay. After I choose a band to go first, how many are left? 2. So how many choices do I have to go second? 2. After I choose who goes second, how many are left? 1. And so that last band that's left by default is going to go third. And so now we multiply those choices together, and you have 6 ways that you can arrange the order of the bands at the concert. And that's if the Rolling Stones go last. So notice that this time my numbers went down by however many choices I had left. So that's important. And notice that I didn't have any blanks. I didn't have any spaces that were left blank. You will always have a number that goes in one of those spots. So that's something to keep in mind when you're doing this. This is just my explanation of what I just did in words. Okay, so there's 6 different ways to arrange the concert. Here's another example. You need to arrange 7 of your favorite books along a small shelf. How many different ways can you arrange the books, assuming that the order of the books makes a difference to you? Okay, maybe you want to arrange them by author. Maybe you want to arrange them by title. Maybe you want to arrange them by the color of their spine, okay, because of how nice it looks on the shelf. But notice that it's the same 7 books, and you're making different arrangements each time you make that decision. So how many books are, let's say this is your shelf here. How many books are going on here? 7. So you have 1, 2, 3, 4, 5, 6, 7 books that are going on here. Did it say that any one particular book had to go in a certain spot? No. So how many of those books do you have to choose from to go first? 7. Once you place a book on the shelf, how many do you have left? 6. Once you place the next book, you have 5, and then 4, then 3, then 2, then 1. Notice none of your blanks, none of those spaces were left blank. You multiply your numbers together. And what does that equal? 5,000? Yeah, okay, so 5,040 ways that you can put the books on the shelf. Notice that that last problem had a pattern. It started with 7, then went down to 6, 5, 4, 3, 2, 1. In the last one, it didn't necessarily, you know, it almost looked like that. It had 3, 2, 1, but it had an extra 1 in there. When you start with the highest number and you go down to the next consecutive integer down to multiply, it's called factorial notation. If n is a positive integer, the notation n with an exclamation mark. So if you have an exclamation mark after your number, that's a shorthand way of saying, I want you to multiply that number along with all of the next consecutive numbers going down to 1. So we just saw 7 factorial. And that's how you say that. 7 with an exclamation mark, you would say 7 factorial. And that meant 7 times 6 times 5 times 4 times 3 times 2 times 1, which gave you 5,040. If you had n factorial as our general case, notice you're going to start with n, then the next number would be n minus 1, then the next number would be n minus 2, because it's 2 away from that original number, until you get down to 1. So you're using this pattern assuming that the number was higher than 3. Okay, it's not always going to be 3, 2, 1. If the number's 3, then you just have 3, 2, 1. If it's 2 factorial, it's just 2 times 1, and so on. But you're counting down until you get to 1. So 5 factorial, 5 times 4 times 3 times 2 times 1 is equal to 120. Now the tough one to sort of wrap your mind around is 0 factorial. And so 0 factorial is equal to 1. Now I know this is hard for you to think because you're not really multiplying by 0, so you don't get an answer of 0. You are actually saying how many ways can you put 0 items into, you know, there's one way to have nothing. Let's put it that way. Okay, there's one way to have nothing. So that's how you can sort of think about that. But if anything, just memorize that 0 factorial equals 1 if you have a hard time understanding that concept. Okay, so all the permutations that you have, you can use that filling in the blank method that we did, but there's also a formula that gives you a shortcut method of doing it. And so we call them permutations. Again, it's arrangements where order makes a difference. And if you're taking r items from a group of n items, then you can write it like this. Now, I don't want you to focus on this long thing on the right. This is the actual formula right here. So capital P with a number in front and a number in the back. The first number is the total number of items that you have in your group. The second number is how many you're taking at a time. So let's say you have 26 letters, but you just want to group 3 letters at a time. It would be 26, capital P, and a 3. And so the formula to work this out is your n factorial over n minus r factorial. So the total number of items is your factorial in the numerator. Then take the difference of those two numbers and find that factorial. Now, the second part of this formula right here is the pattern that occurs every time you do a permutation. You end up having the total number times the next number times the next number until you get to one more than the bottom number. Notice n minus r is your denominator. It'll always count down to one more than that denominator. And I'm going to show you why that happens. All right, let's say that you have a permutation of 10 items choosing 7 at a time. So this means you have 10 factorial over 10 minus 7 factorial. Now, order of operations is very important here. They're not just going to have you work the formula. They're going to have you work lots of different things with exclamation marks, with parentheses, without parentheses. So if you see a parentheses, remember that you have to do what's inside parentheses first. So 10 minus 7 is 3. So you have 10 factorial over 3 factorial. Okay, what this really means is that you have 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1 over 3 factorial, which is 3 times 2 times 1. All right, being that we have a fraction, what can we do with the 3, 2, 1 on top and bottom? Cancel them out. And so the denominator is always going to cancel with part of the numerator. And notice that what you have left is 10, 9, 8, 7, 6, 5, 4. Notice that the last number 4 is 1 more than the denominator. So that's what this pattern means on the right, is that it always ends up being those numbers that you have left. Now your calculator does have an exclamation mark in it if you have a scientific calculator above, but your calculator cannot do big numbers with an exclamation mark. So you have to understand what this concept means of factorial, because you need to be able to do, some of these things without your calculator. Okay, so if we multiply all this together, what do we get? 10 times 9 times 8 times 7 times 6 times 5 times 4. 604,000, so 604, 800, like that? Okay, so 604,800. So that's how many ways that you can create groups of 7 out of a group of 10 items. There's that many different ways you can arrange those items. All right, let's say that some of your items are identical. Okay, the number of permutations of n items where p items are identical, q items are identical, and r items are identical. Okay, let's just say that you had a deck of cards, but they're not standard cards. Let's just say you had 3 red cards, 2 yellow cards, and 5 blue cards. Notice that if you arrange those cards in a certain order, you really wouldn't know that you'd have a different arrangement if all you did was change the order of the 2 red cards. And so that really makes the same arrangement as far as pattern goes, if you're trying to create how many different patterns, if you want to look at it that way. So instead, you're going to modify your formula to look like this. You're definitely going to have your total on top, same as the other formula, but instead of dividing by the difference of the factorial, you're going to put the amount of identical items factorial first, the amount of the next identical items, and so on. Okay, the example I gave you was that you had 3 red cards, 5 blue, and 2 yellow. So how many total cards do you have? 3 red, 5 blue, and 2 yellow. What's the total? 10. Okay, so 10 is the n. The 3 red would be your p, the first amount of identical items. The 5 blue would be your q, the next group of identical, and the yellow would be your r. Now, you don't always have this many numbers in the denominator. It all depends on your problem. How many groups of items do you have that are identical? So you would have 10 factorial over 3 factorial, 5 factorial, 2 factorial. Now, if we expand this out, you have 10, 9, 8, 7, 6. Now, I could write 5, 4, 3, 2, 1, but what's going to happen with that 5, 4, 3, 2, 1? It's going to cancel with this 5, 4, 3, 2, 1 in the middle, right? So I can stop at my highest factorial because I know it's going to cancel with the one that's listed on the bottom. I still have to expand out my other ones, though, because those 5, 4, 3, 2, 1 is going to be gone. It can't cancel again. So I'm going to expand out the 3, 2, 1, and then the other 2 factorial, which is 2 times 1. So there's my 3 factorial, my 2 factorial, my 5 factorial. These cancel as a shortcut. Then I can cancel some more stuff. What's 3 times 2? 6. So 3 times 2 together can cancel with that 6 up top. And then 2 can cancel with the 8, giving me a 4. So now all I have left to multiply is 10, 9, 4, and 7. And what's my final answer here? Ten, 9, 4, and 7 multiplied together. 2520? Okay, so because some of these items were identical, there's only 2,520 ways to arrange them if you use all of the items.